Assalamu alaikum wa rahmatullahi wa barakatuh. I am Sulaiman al-Zahrani, student from King Abdulaziz University. Today, I will talk about ionization chamber. Now, I will talk about introduction to the ionization chamber. The ionization chamber is the simplest type of gas-filled radiation detector and is widely used for the detection and measurement of certain type of ionization radiation, including X-ray, gamma rays, and beta particles. Conventionally, the term ionization chamber refers exclusively to those detectors which collect all the charges created by direct ionization within the gas through the application of an electric field. It only uses the discrete charge created by each interaction between the incident radiation and the gas. Gaseous ionization detectors include ionization chambers and devices that use gas multiplication, namely the proportional counter and the Geiger counter. Ion chambers have a good uniform response to radiation over a wide range of energies and are the preferred means of measuring high levels of gamma radiation. They are widely used in the nuclear power industry, research labs, radiography, radiobiology, and environmental monitoring. A gas ionization chamber measures the charge from the number of ion pairs created within a gas caused by incident radiation. It consists of a gas-filled chamber with two electrodes known as anode and cathode. The electrodes might be in the form parallel plates. Parallel plate ionization chambers or cylinder arrangement with a coaxially located internal anode wire. A voltage potential is applied between the electrodes to create an electric field in the filled gas. When gas atoms or molecules between the electrodes are ionized by incident ionizing radiation, ion pairs are created and the resultant positive ions and discoated electrons move to the electrodes of the opposite polarity under the influence of the electric field. This generates an ionization current which is measured by an electrometer circuit. The electrometer must be capable of measuring the very small output current which is in the region of femtoamperes to picoamperes. depending on the chamber design, radiation dose, and applied voltage. Each ion virus graded deposits or removes a small electric charge to or from an electrode, such that the accumulated charge is proportional to the number of ion virus created and hence the radiation. This continual generation of charge produces an ionization current, which is a measure of the total ionizing dose entering the chamber. The electric field is sufficiently strong to enable the devices to work continuously by moving up all the ion virus, preventing the recombination of ion virus, which would diminish the ion current. This mode of operation is referred to as current mode, meaning that the output signal is continuous current and not a pulse output as in the cases of the Geiger-Müller tube or the proportional counter, because the number of ion virus produced is proportional to the energy of the incident radiation. This continuously measured current is proportional to the dose rate, energy deposited per unit time in the ionization chamber. Referring to the accompanying ion wire collection graph, it can be seen that in the ion chamber operation rig 1 the charge of collected ion wire is effectively constant over a range of applied voltage, as due to its relatively low electric field strength, the ion chamber does not have any multiplication effects. This is in distinction to the Geiger-Müller tube or the proportional counter, where the secondary electrons and ultimately multiple flanges greatly amplify the original ion current charge. Schematic diagram of a parallel plate ion chamber showing gradation of ion virus and drift of ion due to electric field. Electrons typically drift 1000 times faster than positive ion due to their smaller mass. Visualization of ion chamber operation. An incident radiation particle leaves an trail of ion virus in its path as it travels through the gas and collides with gas atoms. Each ion wire consists of a free electron, which is attracted to the anode, and a positive ion, which is attracted to the cathode by the influence of the electric field. This movement is known as ion drift and ensures that the electrons and positive ions don't recombine and that an ionization current is generated, proportional to the number of ion wires created. Plot of ion current against voltage for a conceptual wire cylinder gaseous radiation detector. Ion chambers use the lowest voltage plateau. Plot of relative level of ion wire current with increasing voltage applied between anode and cathode for a wire cylinder ionization detection system with a constant incident ionizing radiation. This covers the practical areas of operation of the Geiger-Müller counter, the proportional counter, and the ionization chamber. Alpha particles are more ionizing than beta particles, so more current is produced in the ion chamber rig 1 by alpha than beta. but the particles cannot be differentiated. More current is produced in the proportional counting region by alpha particles than beta. But by the nature of proportional counting, it is possible to differentiate the alpha and beta pulses. In the Geiger region, there is no differentiation of alpha and beta as any single ionization event in the gas results in the same current output. Note that gamma and X-ray photons result in the same plot chap. Current also being dependent on radiation energy. Now I will talk about chamber types and construction. Number 1. Free air chamber. This is a chamber freely open to atmosphere, where the filled gas is ambient air. The domestic smoke detector is a good example of this, where a natural flow of air through the chamber is necessary so that smoke particles can be detected by the change in ion current. Other examples are applications where the ions are created outside the chamber but are created in by a forced flow of air or gas. Number 2. Vented chamber. These chambers are normally cylindrical or operate at atmospheric pressure, but to prevent increase of moisture, a filter containing a discant is installed in the vent line. This is to stop moisture building up in the interior of the chamber, which would otherwise be introduced by the pump effect of changing atmospheric air pressure. These chambers have a cylindrical body made of aluminum or plastic a few millimeters thick. The material is selected to have an atomic number similar to that of air so that the wall is said to be air, equivalent to other a range of radiation beam energies. This has the effect of ensuring the gas in the chamber is acting as though it were a portion of an infinitely large gas volume, and increases the accuracy by reducing interactions of gamma with the wall material. The higher the atomic number of the wall material, the greater the chance of interaction. The wall thickness is a trade-off between maintaining the air effects with a thicker wall and increasing sensitively by using a thinner wall. These chambers often have an end window made of material thin enough, such as mylar, so that beta particles can enter the gas volume. Gamma radiation enters both through the end window and the side walls. For handheld instruments, the wall thickness is made as uniform as possible to reduce photons directionality through any beta window response is obviously highly directional. Vented chambers are susceptible to small changes in the efficiency with higher pressure, and correction factors can be applied for very accurate measurement applications. Number 3. Sealed low pressure chamber. These are similar in construction to the vented chamber, but are sealed and operate at or around atmospheric pressure. These chambers also have the advantage of not requiring a vent and descent to improve detection efficiency. They are filled with a noble gas because the highly electronegative oxygen in air easily capture free electrons, forming negative ions. The strength of the beta window limits the differently pressure from atmospheric pressure that can be tolerated, and common materials are stainless steel or titanium with a typical thickness of 25 micrometer. Number 4. High pressure chamber. The efficiency of the chamber can be further increased by the use of high pressure gas. Typically, a pressure of 8 to 10 atmospheres can be used, and various noble gases are employed. The higher pressure results in a greater gas density and thereby a greater chance of collision with the file gas and ion barrier creation by incident radiation. Because of the increased wall thickness required to withstand this high pressure, only gamma radiation can be detected. These detectors are used in survey meters and for uniformitary monitoring. Number 5. Research and calibration chambers. Early versions of the ion chamber were used Marie and Pierre Curie in their original work in isolating radioactive materials. Since then, the ion chamber has been a widely used tool in the laboratory for research and calibration purposes. Now I will talk about the chamber's applications. Number 1. Applications in nuclear industry. Number 2. Smoke detectors. Number 3. Medical radiation measurement. The specialty is important now. Let me talk about it. Medical radiation measurement. In medical physics and radiotherapy, ionization chambers are used to ensure that the dose delivered from a therapy unit or radiopharmaceutical is what is intended. The devices used for radiotherapy are called reference dosimeters, while those used for radiopharmaceuticals are called radiostop dose calibrators, an inexact name for radionuclide radioactivity calibrators. which are used for measurement of radioactivity but not absorbed dose. A chamber will have a calibration factor established by a national standard laboratory such as Urbansa in Australia or the MPL in the UK, or will have factor determined by conversion against a standard chamber trackable to national standards as the user's set.